Welcome to the video Directional Derivatives and Linear Approximations. In this video, we will discuss the directional derivative of f at a point P in a direction given by u hat, and we'll explain and see examples of this type of formula. And we also want to look at linear approximations, which are given by this type of formula. So we will see where this comes from later in this video. For these two things, we could have, for this first one, we could have a picture like what we have over here. Here is the xy plane, the x-axis being horizontal, the y-axis being vertical. We have a point P, which for instance could be the point with rectangular coordinates 1, 2, and we have a vector of length 1. A unit vector pointing in some direction. These are the things we need in addition to knowing the formula for the function f of xy in this case, so that we can evaluate directional derivatives and do some linear approximations. This linear approximation is similar to what you may have seen in a Calculus 1 course for a function of one variable. But here we could look at functions of 2 variables, 3 variables, or more. In this particular video, we will concern ourselves only with functions of 2 variables, but what we say does generalize to more variables, multidimensional spaces. First, let's recall what we saw in a previous video. So, in a previous video, we considered this problem. Let f of xy be x squared plus y squared. Let u hat be this unit vector. And look at the point P equals 1, 2. This is a point in the xy plane. Calculate the directional derivative of f in that direction u, evaluated at that point P, 1, 2. So if we write it out explicitly, we get this. So what we're trying to do here, remember, is starting at the point 1, 2, find the instantaneous rate of change of f in the direction of that unit vector. Here's a picture. It's totally a two-dimensional problem. Here are the x and y axes. Somewhere in the xy plane is the point 1, 2. We have a vector u hat, which is given by these components, and we want to find out how fast the function f is changing as we move in the direction pointed to by this vector u hat. So now we're going to change our perspective. Instead of looking at things in 2 dimensions, we're going to consider 3 dimensions. So here is a picture in 3 dimensions of a similar situation. We're still looking at a function f of xy equal x squared plus y squared, but we're going to look at the surface z equals x squared plus y squared. This surface is represented in 3-dimensional space, and if we plot it, it turns out to be a paraboloid. It's something like a 3-dimensional analog to a parabola. We want to find a tangent line to this surface at the point with coordinates x, y, and z, 1, 2, and 5. So this is what we're after. We have a surface, z equals f of xy is equal to x squared plus y squared. It's this paraboloid that we see here, something like a 3-dimensional analog of a parabola. And on this surface, somewhere, right about here, is the point whose x, y, and z coordinates are 1, 2, and 5. We want to find a tangent line to this surface at this point. So here is the illustration of this tangent line. This tangent line only touches this surface at the point 1, 2, 5. It's kind of analogous to the two-dimensional problem of finding a tangent line to a parabola, but here we're finding a tangent line to this paraboloid, this surface. Now, it turns out that there are many different answers to the question, find a tangent line to this surface at this point. Here is that same paraboloid, and you can see some lines emanating from somewhere on the other side of that paraboloid. Let's turn this paraboloid around to see what's going on. What we have here basically right here is the point 1, 2, 5, and we have lots of tangent lines coming out in different directions. All of these lines, each of these lines is tangent to this paraboloid surface at the point 1, 2, 5. So the solution to our problem is not unique. So we want to narrow down the problem so that it has exactly one solution. So here is the paraboloid again. Here is the point 1, 2, 5, and we saw that there are many tangents to that surface at that point 1, 2, 5. So we're going to narrow it down the following way. In a previous video we showed that the directional derivative of f at the point 1, 2 in the direction in the xy plane, 1 over square root of 2, 1 over square root of 2, that unit vector, turns out to be 3 times the square root of 2. So we're going to specify that we're looking for the equation of the three-dimensional tangent line t to the surface point, to the surface at the point 1, 2, 5, corresponding to the horizontal direction of the unit vector u hat, which is this, the same as when we found the directional derivative up here in the direction u hat. And what that means is that the x and y components of this vector t that we're looking for should be 1 over the square root of 2, 1 over the square root of 2. Remember that t is a vector in 3 space. It'll have 3 components, and so basically all we're left with is finding that third component, the z component. Okay, so we have that z equals f of xy equals x squared plus y squared. We have this formula for approximating f at the point P in the two-dimensional plane plus a little bit of a increment delta t times a unit vector u. And we saw that in a previous video was approximately f of p plus delta t times this directional derivative. This was analogous to the approximation formula that you had in Calculus 1, and if you remember, that approximation formula, that linear approximation formula, gave us the equation of the tangent line to a curve at a point. But now we're doing this in 3 dimensions, and so we're trying to find a tangent line in a certain direction to a surface at a point on that surface. So using this formula, with p equaling the value, the point in the xy plane 1, 2, and letting u be 1 over the square root of 2, 1 over the square root of 2, that unit vector that we saw before, just plugging into this formula gives us the following. Now, one thing, going from this equation up here to this one, I decided, since I'm not just looking at a small increment delta t, I want to find the tangent line approximation. I'll replace that by t, where t can be any number, small or large. And so f of 1, 2 plus t times this unit vector we talked about before is approximately equal to 5 plus t times this derivative, which was the square root of 3 over 2. Now, remembering that we have in 2 dimensions an x-axis and a y-axis. We have a point here, which is the point x, y equals 1, 2. This is the x and y coordinates of this point here. And here's our unit vector in the direction 1 over the square root of 2, 1 over the square root of 2. We'll set up a t-axis along this vector, and we'll let t equals 0 be right here at this point, t equals 1, t equals 2, t equals 3, t equals 4, and so forth. And what we want to do is to pick some point on this t number line, and let's let it be x of t, y of t. In that case, using this formula right here, this stuff right here is going to be the height of that paraboloid above this particular point, and we'll call that height, in the positive z direction in this case, z of t. So this stuff is z of t equals 5 plus t times 3 times the square root of 2. So that's what we have right here. Remembering also that this point is in the xy plane, and this point right here has coordinates 1, 2 in the xy plane. Then we can say that this point x of t up here has to be 1 plus the square root of 2 over 2 times t, and the y coordinate is 2 plus 1 over square root of 2 over 2 times t. That's because this point is the point 1, 2, and that explains why the 1 and the 2 are here. And if we move a distance t along here, then the x change and the y change are both going to be the square root of 2 over 2 times t. So we have formulas here then for x, y, and z for that line in 3-dimensional space, that tangent line that we're looking for. So writing this system of equations in vector form, we can say that the equation of the desired tangent line to that paraboloid surface is given by this position vector, x, y, z equals the vector 1, 2, 5 plus t times the square root of 2 over 2, square root of 2 over 2 times 3, square root of 2. This part right here just comes from this stuff right here. So we have solved the particular problem that we were looking at, which was to find that particular tangent line to that surface that went through the point 1, 2, 5 and was tangent to that paraboloid in the direction of u in the xy plane, u being that unit vector 1 over the square root of 2, 1 over the square root of 2. Here we have a graph of the tangent line to that paraboloid versus the unit vector u. This black line is the tangent line. This red line down here is the vector u, which is in the xy plane. So what we first notice is, looking at this tangent line, right here is the point 1, 2, 5, which was the point of tangency with that paraboloid. The x-coordinate, this is the x-axis, remember, the x-coordinate of this point is 1. The y-coordinate is what? Well, here's 2 on the y-axis, so right over here we have the point 1, 2, 0, and if we go up a distance 5 here, we have the point with coordinates 1, 2, 5. Now, graphing this, we made the slope m equal to 3 square root of 2, and down here for this unit vector u, this is in the xy plane, so the slope of this vector is, if you think of it in 3 dimensions, the slope is going to be 0. Now, if we drop perpendiculars down to the xy plane, from this point down, it'll come down here, and from this point up here, right at the tip actually, coming vertically down to here, we have right angles right here and also right here. because this line is in the XY plane. It's in the horizontal XY plane. These two lines we're dropping down to the XY plane are vertical. These are right angles. So what happens is the projection of this tangent line down to the XY plane is just going to go along this unit vector u, or a multiple of it if we went out perhaps further out here. This is only part of the tangent line. It keeps going in this direction, also down this way. So what we have for this tangent line is kind of a copy of this unit vector, at least shown in this diagram, but then we gave it a slope upward in the z direction. As we go out along this line, the z-coordinate increases and increases and increases, and in this cross section we would have that the slope is 3 square root of 2. For every unit 1 that we go along this vector, unit vector, which is actually right out to here, we're going to go up 3 square root of 2 in this direction. It doesn't look like this is really 3 square root of 2 until you notice that the units on these three axes are not the same. This one goes from 0 to 10 for the z-axis, 1 to 1.8, maybe 2 here, and for the x-axis, and 2 up to at least 2.8 in this y-axis. So in any case, we can see what that tangent line looks like compared to that unit vector in the xy plane. We don't have the paraboloid shown here, but I think that would probably complicate the picture, so it would be very hard to see what's going on. And here we have the program to draw the paraboloid and also that one tangent line in the direction 1 over the square root of 2 over 2, 1 over the square root of 2 over 2. If we look at this program, this part of the program right here is going to draw the paraboloid, and the part down here is going to draw the tangent line. We saw the paraboloid part before, I believe, but if we look at what we have here, we can see that x, y, and z are going to be points on the tangent line, and they're given by the vector 1, 2, 5 plus a multiple k minus 4 times 1 over the square root of 2, 1 over the square root of 2, and 3 times the square root of 2 for the z direction. Then we plot the whole thing, x1, y1, z1, the tangent line in red with a line width of 2. We have a hold on somewhere, I guess, right here, so that we plot the surface, and then on the same graph we plot the tangent line. This is the output of the program. Here we see the paraboloid, and this is the tangent line to that paraboloid at the point 1, 2, 5. If we want to, we can rotate this around to get an idea of how that tangent line looks to that surface at that point. So what about the other tangent lines to that paraboloid at the point 1, 2, 5, which is on that paraboloid? We'll find out that we can find one tangent line to that paraboloid at that point 1, 2, 5 for each direction theta in the xy plane, thinking of theta as being the angle in polar coordinates between the x-axis and the unit vector. Suppose we want to find those other tangent lines. What we can do is for each value of theta between, let's say, 0 and 2 pi, we can define a unit vector which I'll call u hat sub theta, which is in the xy plane, and the first component is cosine theta, second component is sine theta. Think of this as being basically in polar coordinates. But this is the x and the y coordinates of that vector. For instance, in the problem that we've looked at so far, if you let theta be pi over 4, then cosine of theta, sine of theta, is 1 over the square root of 2 over 2, 1 over the square root of 2 over 2. So we could ask then, given other values for theta, what tangent to the surface corresponds to that direction specified by this vector, or I guess you can say specified by a direction in polar coordinates. Well, for small t, we saw this formula before. F of a point plus delta t times a unit vector, in this case I'll have u hat sub theta, is going to be approximately f of p plus delta t times this directional derivative. And so what we can do is plug in the things that we know. The point P is 1, 2. And so we're going to be looking at this stuff right here. So we have P plus delta T times the unit vector, which is right here. And that's approximately equal to f of P, which is f of 1, 2, plus delta T times this direction, the derivative in the direction u naught of f, that derivative at that direction evaluated at f of 1, 2. So let's look at the derivative of f, the directional derivative of f in the direction u naught, u sub theta. So by definition, this is going to be the limit as delta t goes to 0 of this difference quotient. P is the point where we're finding the directional derivative of f. U is actually this u sub theta here, is the direction we're going in. And so we have this minus this over this. This looks a lot like the definition of a derivative that you saw in Calc 1, except now we can go in any direction we want, in this case in the xy plane. So we plug in what P is, 1, 2. We plug in what the unit vector is, cosine theta, sine theta. We subtract f of P, which is f of 1, 2, divided by delta t. So when we write all of this stuff out, we get this. Remembering that f of xy is x squared plus y squared. So f of 1, 2 is 1 squared plus 2 squared. So far, I just left f of this the way that we had it up here. But now we can write out what f of all this stuff is. It's this x component squared plus this y component squared. And then we have all the rest of the stuff as before. Now, when you take this binomial and square it, you'll get 3 terms. When you take this binomial and square it, you'll also get 3 terms. But the first term over here is going to be 1 squared, which we subtract off here. The first term, when you expand this, is going to be 2 squared, which we subtract off here. So the only terms that are left are 2 terms from here and 2 terms from here. So I claim that this now equals 2 cosine theta plus 4 sine theta. Why? Well, if we divide 2 times delta t times cosine of theta and divide that by delta t, we're just left with 2 cosine theta. Over here, let's just skip this one for a second. Over here, 4 delta t times sine theta divided by delta t gives us 4 sine theta. Okay, so what happens to the other two terms in the limit? Hopefully they go to 0. Well, if you look at this, you're squaring it. So that's going to give us a factor of delta t squared divided by delta t. Still gives us, for this over this, a factor of delta t, which goes to 0. So this term over delta t goes to 0 as delta t goes to 0. Similarly, this term divided by delta t goes to 0. So you're only left with 2 cosine theta plus 4 times sine theta. So we have seen the formula for approximating f of 1, 2 plus a small increment. This is an approximation, a linear approximation, f of 1, 2 plus t times this directional derivative. This is slightly different from the last slide. Instead of using delta t's, which I assume are going to be very small, here I use t's, which can be any value. This approximation is only good, most likely, for very small values of t. But this is going to be, on this side at least, our linear approximation to that surface on particular a curve embedded in that surface. And we found out that that directional derivative at 1, 2 is equal to this stuff. So then what we can say is, well, z of t is going to be 5 plus t times that directional derivative. And that directional derivative was equal to this. X of t is just going to be 1 plus t times the first component, x component of our unit vector cosine u. Y will be 2 plus t times the y component of that unit vector, which is sine theta. So basically, putting these three things together, we get that x, y, z is what? This stuff was x, this stuff right here was y, and this stuff right here is z. So now if we just rewrite this formula using a little bit more vector notation, we can easily write it in the form the vector with components x, y, z equals the vector with components 1, 2, 5 plus t times this vector, cosine theta, sine theta, 2 cosine theta plus 4 sine theta. And so this gives us basically the tangent line to that surface in the direction of u sub theta. This tangent line touches the paraboloid at the point 1, 2, 5, and at least as far as the direction given by the directional derivative, it has that same direction as far as the x and y components go, but the z component has to take into account the slope of the tangent line as you move in the direction of u sub theta. So here's the program that can produce all of those tangent lines that we saw before. We first clear things and close the figures if any existed already. This first part of the program we have seen before. This is the part that plots the paraboloid. And now the second part of the code down here is going to plot all of those tangent lines. This code looks much like what we had before also for that one particular tangent line parallel to the vector 1 over the square root of 2, 1 over the square root of 2. But in this case, we're going to use the unit vector with components cosine theta, sine theta. So this code looks similar before, except here we would have had 1 over the square root of 2. Here we would have had 1 over the square root of 2. But in this case, we want to look at other angles too. So we have a loop here that goes for theta, goes from 0 to 2 pi by increments of pi over 16. We compute this tangent line and then we plot it. So we do this, it looks like, what, maybe 32 times to get 32 tangent lines, and each one we plot. The hold is on right here, so when we plot the second tangent line, the first tangent line stays on the screen, and after all 32 of these tangent lines to that surface at 125 are plotted, we get out of the loop, we turn the hold off because we don't need it anymore, and then we can view the graph as we wish. When we run that program, we generate this paraboloid once again. Looks like this was done with a surf command possibly, and also generates lots of tangent lines to this paraboloid at the point 125, which happens to be on the other side of this surface, which is obscured on this side by the paraboloid. So what we have seen is that we can find tangent lines to the surface pretty easily with a geometric computation involving vectors. We are able to plot these things easily using MatLab, and we can apply this technique to other problems too. You might remember when we rotated this diagram before, we were able to turn it around and see all of these tangent points emanating from what appeared to be one point on the surface. And as we rotated, you might have also noticed that all of these tangents to the surface at that one point, 125, seemed to lie in perhaps a flat plane. Well, in fact, those tangent lines do lie in a flat plane, which is called the tangent plane to this surface at that point 125. So another problem we might want to consider is, for another video, how can we find that tangent plane? To do that, we'll have to talk a little bit about equations of tangent planes and do a little bit more geometry to get the solution to that sort of problem, finding the tangent plane. So in summary, we saw that the directional derivative of f in the direction of some unit vector u, this directional derivative evaluated at a point P in the xy plane could be written this way. We saw that this represents the instantaneous rate of change of f in the direction of that vector u. We then saw that we could look at f of p plus a small change approximately being equal to f of p plus this change involving the directional derivative. And the left-hand side of this allowed us to find the equation of the tangent line to the surface at the point in our particular problem 125, which is 1, 2, and then the 5 is f of 1, 2. We can use this technique in general to find tangent lines to surfaces, and we saw that a surface can have lots of tangent lines at a point. In fact, an infinite number of tangent lines. And in later videos, we're going to ask how can we use the gradient, which we haven't defined yet, to calculate these directional derivatives and tangent planes. We haven't talked about how to find planes yet. How can we use tangent planes to estimate the value of a function at x plus delta x, y plus delta y, assuming you know what the value of f of x, y is, delta x and delta y small. And can all of this that we're doing help us with problems involving different non-Cartesian coordinate systems, such as polar coordinates? Thank you for watching this video. I hope you enjoyed it. Please stay tuned for more.